kind of transformation as invertible transformation. So here, so we have two vector spaces, V and W. Okay, and in V and W we have in vector space V we have a vector X, and in vector space W we have a vector Y, and so there's a transformation we call it as T, and so that T sub X equals Y, and on the other hand, there's another transformation we call it as T inverse. So that if we apply T inverse on vector Y, then we can get X in the vector space V. Okay, so that maybe I'll just put U here before we call it as inverse. So we will put the transformation U here. Okay, so in this scenario, so that if we can have, okay, we transfer the vector from X to W, so Y equals T sub X, and then we can from this equation we can see that, okay, you can write it as, it becomes U sub Y, because Y equals T sub X, so I can write it as T sub X here. And then I can, because this is a composition of linear transformation, so we have UT sub X. And this composition of linear transformation, because whatever vector in X, after transformation, we get the vector back to X, so we can call it as identity transformation of X. So now we have UT equals IV. We have UT equals IV. So the composition of linear transformation of UT, which will be equal to the identity transformation in vector space V. And in addition, we also know that because X, here, Y equals T sub X. But here we know that T sub X, Y equals T sub X, but X equals U sub Y. So we have T operates on the vector U sub Y. U sub Y. Okay, then from the same argument, we have TU, the composition of linear transformation, on transform the vector Y. Transforms the vector Y. So we can find that, okay, go this way, if we go this route from here to here, then we find that, okay, this is an identity transformation in vector space W. So then we have TU equals IW. So if this is true, then we call this linear transformation U as the inverse transformation of T. So we denote it as T inverse here. Okay, so we denote it as inverse here. So from the definition here, we have let V and the W be vector spaces, and the T is a linear transformation from V to W, which will be linear. And a function U, another transformation, which transform the vector from W to V. We say that this transformation we assume it's a linear transformation, and we say it's an inverse of T if TU equals IW. So if TU, the composition of linear transformation, equals the identity transformation in W, and the UT, the composition of linear transformation of U and T, which will be equal to the identity transformation in V, then we call this this transformation as an inverse of T. So then, if T has an inverse, then T is said to be invertible. Okay, and we denote it as T to the minus 1 order. Okay, so here in this definition, we have a lot of things to be discussed. So first of all, for this invertible transformation, a very important thing is that, okay, when we do the linear transformation, actually for every linear transformation, we operate the vectors in the vector space V, all the vectors in the vector space V. So we cannot let any vector in vector space V which cannot be converted to W. So all the vectors in V. So if we do the reverse transformation, the inverse transformation, we will also operate all the vectors in W. So you will transform the vector from W to V for all vectors. So this statement is very important because we will be using this statement later. Okay, so here from what we defined, then we need to prove a lot of things here. So first of all, we need to prove that this kind of inverse transformation, if T is invertible. If T is invertible, then we need to prove, the first thing is that we need to prove that T should be 1 to 1 and on 2. The transformation should be, if it's invertible, then the transformation should be 1 to 1 and on 2. So here we define what is 1 to 1 and on 2. So for 1 to 1 in a function is defined as a function from domain A to codomain B, and then fx equals fy implies x equals y. If x is not equal to y, then fx is not equal to fy. So which means that for 1 to 1, we have two criteria here from vector space V to vector space W. If it's 1 to 1, then x is not equal to y. If x is not equal to y, then after transformation, Tx will not be equal to T sub y. So that is the first, if x is not equal to y, then fx is not equal to fy. And also, in vector space V to W. Okay, if we have T sub x equals T sub y, which means that in this transformation, x should be equal to y. So we have two statements, two facts for 1 to 1. So the first fact is that if from the codomain, if the codomain value is identical, then the value in domain should be identical. If the value in domain is not identical, the function in the codomain is not identical. So we have to, for 1 to 1, we have to know these two facts. And then for on2 says that on2 in the function is defined by the function from domain A to domain to the codomain B, and then fa equals b, such that all the values in domain B can be found the corresponding value in the domain A, so that all the value in domain B will be covered by this function from domain A. So for on2, on2 means that if I have a vector space V and if I have a vector space W, when I transform the vectors from V to W by linear transformation T, the range of T will be equals to W. So if I can have this this phenomenon, then we call that this transformation is on 2. Okay, so right now, what we are going to do is that, okay, for this invertible transformation, if T is invertible, then we need to prove that T is 1 to 1 and on 2. Okay, so we first prove that A T is 1 to 1. Okay, we need to prove that T is 1 to 1. Okay, so right now, if we want to prove that T is 1 to 1, we have to prove either Ts is not equal to T sub y, S should not be equal to y, or so we can prove it in this way. So then, because T is invertible, then we can assume any vector y in vector space W, and but y is not belong to range of T. So in this scenario, we have vector space V and a vector space W. We have T, this linear transformation is invertible, but after transformation, the range of T, we have already know that range of T should be contained in vector space W, because range of T is a subspace of W. We have already learned it. And right now, if this, this is for prove the, this is to prove the on 2. Sorry, I'll prove the on 2 first. Sorry, here. Okay, follow my note here. So if we want to prove it on 2 first, then we assume that any vectors y belongs to vector space W, but y is not in the range of T. So we may say that y is here. Okay, we may say that y is here. And because T is invertible, so we also have inverse of T. Okay, we also have inverse of T. So right now, we can assume, so because we have inverse of T, so T inverse of y, if we inverse a function, a vector y from W back to V, then we know that T inverse y should be belongs to V. Okay, T inverse of y should be in V. Then if we take the linear transformation again, well, I will get, because T is invertible, so then we get it equals y. So we get this one equals y, but here, because inverse transformation of y belongs to V, so when we do the transformation, we do the transformation on any vectors in V, such that all the transformed vectors should be within range of T. So this is in the range of T, because this one is in V. Okay, and we exist the vector y after inverse transformation, it should be in the vector space V. So by doing this transformation, by doing this composition of linear transformation, then we get the y should be in range of T. So this assumption is not true. This assumption is not true. And in this proof, because we have already assumed any vector y in W, And then we do the inverse transformation. We do the compositional linear transformation. And we know that, okay, T's inverse transformation of Y should be in V, and then Y is in range of T. So any vector in Y is also in range of T. So we have range of W should be covered by range of T. But we have already known that range of T should be a subspace in W. But from here, any vector Y in W is also in range of T. So W is covered by range of T, and the range of T is covered by W. So then we have range of T equals W, which means on 2. Okay. So we have first proved that this transformation is on 2. And then we want to prove T is 1 to 1. We want to prove T is 1 to 1. And then we also, because T is invertible. Because T is invertible. So we let UTS equals X. Okay. So right now we want to prove that it's 1 to 1. So we want to prove that if T sub X equals T sub Y, but X is not equal to Y. So this is the way we prove the 1 to 1, because we know that if T sub X equals T sub Y, means that in the vector space that V, X should be equal to Y. So this if this statement holds, then it's 1 to 1. Okay, so right now we just use the contradiction approach to prove it. So if we assume T sub X equals T sub Y, but X is not equal to Y, so right now we can see that it's 2 to 1. Because from this assumption, it's 2 to 1. i.e., that is to say 2 to 1. It's not 1 to 1. Okay? So if we assume it's not 1 to 1, then what we're going to do is that, okay, so what we're going to do is that, okay, so then we say that from here, because you use the inverse transform of T, so UT sub X here, well, X will be equal to UT sub X. So here, UT sub Y equals Y, okay, because T is invertible. Then we have UT sub X, because we have UT of X equals UT sub Y, so it equals UT sub Y. So then it will be equal to UT sub Y. And this is the identity transformation, is IV, IW, sorry, from, okay, it's IV, sorry, IVY. Okay, then we have X equals Y. So from here we know that this assumption is not true. This assumption is not true. So if T sub X equals T sub Y, X must be equal to Y, because T is invertible. So now we have 1 to 1 and on 2, this transformation. If the transformation is invertible, then right now we know, so we have already proved that T should be 1 to 1 and on 2. So from T is 1 to 1 and on 2, what do we learn? From the dimension theory, we know that from a dimension theory, if T is 1 to 1, null space of T is 0 vector only. So nullity of T equals 0. So from dimension theory, we know dimension V equals nullity T E plus rank T. the dimension of the range of T from the dimension theorem, okay? But because now the T is 0, so we have dimension V equals rank T. However, T is on 2. T is on 2 means that range of T equals W. So rank of T equals dimension W. So what do we have? If T is invertible, dimension V should be equal to dimension W. So if T is invertible, the two vector space should have identical dimensions. If the dimensions are not identical, there will be no invertible transformation. Okay, so here this conclusion is very important. So whenever we have an invertible transformation, the two vector space should be with the same dimension. Okay, so this is the first thing we need to prove. Okay, then we also need to prove that this inverse transformation of T is unique. So the second fact, so here we have already proved the first fact. T should be 1 to 1 and on 2, and also dimension V should be equal to dimension W. Okay, so T invertible implies 1 to 1 and on 2, and also dimension V equals dimension W. So we have already proved the following fact, the third fact here. But I think this one is the most important, so I prove it first. Okay, and here for the third fact, actually he doesn't in the textbook it doesn't prove they will be with equal dimension. In the third fact, it assumes the two vector space are with the same dimension, but it's not proved. But here we prove it. So here we prove it. So the two vector space should be with the same dimension. Okay, that is the first fact. And the second thing we have to prove is that the second step we need to prove. So here T is invertible. We need to prove the inverse transformation of T should be unique. We have to prove that it's unique. So typically, if we want to prove uniqueness, what do? We assume it's not unique. So let U also equals U also let U let's see okay, let U is also an inverse transformation of T. So we assume it here. Okay, then what do we have? So we let T sub x equals y. So in the vector space V and W, we have y here, which equals to T sub x. And so we have T here. Now we have we have x here. Now we know that T is invertible. So we know that because T is invertible, so we know that x equals inverse transformation of y. And also here we assume we have another transformation U. And we also, because we assume U is also an inverse transformation of T, so we also have x equals inverse transformation, y, the transformation U the transformation u on vector y. Okay, so we have this one. Then, okay, so right now we have x equals u sub y. Okay, and then u sub y equals u sub y equals u sub t sub x, because y is obtained from transformation of x. Then we have ut equals x, ut sub x equals x, and this is an identity transformation of x. So right now we have ut equals inverse t equals iv. So here we have u equals inverse of t. So then, if we assume here, if we assume that u is also an inverse transformation of t, and here u is not equal to t inverse. So because we want to prove the uniqueness, so assume they are not unique. So we have another transformation. We name it as u, and it also operates the vector y back to x. So right now we get this result. So right now we get this result. So u will be equal to inverse transformation of t. So then we prove the uniqueness. Because this statement is not true. Okay, so here from the definition, right now we have already proved that, okay, this transformation t, inverse transformation of t is unique. And also we prove dimension v equals dimension w. And also t is invertible if and only if rank t equals dimension v. Rank t equals dimension v here because of 1 to 1. Okay, so here we have found here we have t is invertible. It implies that rank t equals dimension v, so t is 1 to 1 and on 2. In addition to the dimension of the two vector space should be identical. So which is not proved here, which is an preassumed. For with equal dimension is preassumed. So it's not true here. Okay, now the third fact is that, okay, we want to prove, we want to show that the fact 1 here, so the third fact we have to prove is that, okay, t u inverse equals u inverse t inverse. Okay, so to prove this actually it's quite redundant, but here we just want to use a graph to describe this one. Okay, if I have vector space v and w, and also I put another vector space v here. So if I have a vector x in v, after linear transformation t, after linear transformation we get the vector y here. And after the inverse transformation, okay, sorry, maybe I have to put u here, sorry. I have to put u here. Okay, the following hold for invertible functions, t and u. And we have t here, if it's z. So we have this one to here is, we operate u first, so it should be u t. So right now, what we're going to do the reverse way, we have t u inverse. So from yellow one to the orange one is TU inverse. But we want to inverse it from Z to X. So what we're going to do is that we will have T inverse first. And then we will have U inverse here. Okay, so what we are going to do is that T U inverse on Z will be equal to X. T U inverse on Z will be equal to X. And but if we transform it step by step, then we first transform T inverse Z, which equals to Y. And then we do another linear transformation U inverse, which will transform Y back to X. So now we have T U inverse equals U inverse T inverse. Okay, so we first transform Z back to Y by using inverse transformation of T, and then transform Y back to X, use the inverse transformation of U. If we go it directly, that is the inverse transformation of TU. So then we get this result. And the first one, then if I have inverse, which will be equals to T. So I'm not going to show it again because it's just similar to this diagram. Okay, then the final one is that for the third fact, we have already proved that for the third fact, we say that T is invertible. Okay, so T is invertible if and only if rank T equals dimension V. We have already proved it because we assume T is invertible, so this transformation is 1 to 1 and on 2. So we can get the following result. But right now, because it's if and only if, so we have to prove it in the reverse way. Okay, so the last one, so for the fifth one, we have to prove right now what we have known. Okay, what we have known is rank T equals dimension V. Okay, so rank T equals dimension V, which implies 1 to 1. And also because we have already proved it, I have erased it already. So we have already proved it, rank T equals dimension V and it equals dimension W. So it's also on 2. So right now what we have known is that T is 1 to 1 and on 2. So we are going to prove T is invertible. Okay, so we're going to prove T is invertible. So what we are going to prove is in the reverse direction here. In the reverse direction. So, okay, because of on 2, then we have range of T equals W. Okay, and then, so for any vector, W in vector space W, it can be expressed as T sub V. So maybe I should put that. So there exists V belongs to V such that T sub V equals W. Because of on 2, so I have vector space V, I have vector space W. Because the transformation is on 2, so range of T equals W. So any vector here, W, can find a corresponding vector V in vector space V such that W equals T sub V. So that's from on 2. Okay, that is from on 2. So, and in addition to that, because 1 to 1, so this V is unique. If it's on 2, maybe I have another vector x. We can also map the vector x to ws, which equals to w. If it's not 1 to 1, but on 2. Okay? If it's not 1 to 1, but on 2, then we can, may also find another vector x is not equal to v, such that t sub x equals t sub x equals t sub v t equals w. If it's not on 2, if it's not 1 to 1, but because it's 1 to 1, so for 1 to 1, we know that for 1 to 1, one of the fact of 1 to 1 is that, let's go back to this definition again. For 1 to 1, if f of x equals f of y, implies that x equals y. So if t sub x equals t sub y, that means x equals y. So then it means that v is unique. V is unique. Okay, so right now we have on 2, we use on 2 and the property of on 2 and the 1 to 1. Then what we are going to do is that okay, so there will exist u from w to v, because we want to prove that u is the inverse transformation of t. So we have u from w to v, so that u w equals v, and v belongs to vector space v. So right now because t sub v equals w, so we substitute w as t sub v, so we have u sub t sub v equals v. And then for this part, for the left-hand side, it's ut equals v. Ut sub v equals v. But for v itself, we know it's identity transformation of v. So then that means here, ut equals iv. Ut equals iv. Okay, so we prove ut equals iv. So we have ut equals iv, and but we haven't proved that tu equals iw. So right now we have t sub v equals w. We have already know it. So there will be identity transformation in w sub w. Okay, but because v is equal to t sub u sub w, so we substitute v. We replace v by u sub w. Then we have tu sub w, which will be equal to identity transformation of w. So then we get tu equals iw. So from these two results, we can claim that u is the inverse transformation of t. So t is invertible. Okay, so we prove that the reverse way, if rank t equals dimension v, which means that t is 1 to 1 and on 2, and then t is invertible. Okay, so we have already proved the 5 facts. And the next one is an example. So we have, if we transform a vector, a polynomial, degree 1 polynomial, to two-tupled real column vectors, then we define the transformation by t sub a plus bx because it's a degree 1 polynomial and equals to a plus b. There are two elements in this row vector. And then we can find the inverse transformation if I have C and D. So if I have C and D, and we can follow the same concept, and we can find that, okay, if I have C and D, and then we can find the coefficient A should be equal to C, and the coefficient B should be equal to D minus C. So then we find that the inverse transformation is also linear. Okay, so this one is pretty simple. Then the next one, theorem 2.17. So right now we know that the linear transformation T is invertible, and the inverse transformation is also linear. Okay, so here what we are going to prove is that we have two vector space, V and W. Okay, so here T is linear. T is linear and invertible. So T is invertible. T is linear and invertible. T is linear and invertible. Okay, so here, and so we know that, so right now we can assume y1 and y2 in W. y1 and y2 in W. Because T is invertible, so we know T is 1 to 1 and on 2. So we can find a corresponding vector x1 and x2 in vector space V such that Tx1 equals y1, Tx2 equals y2. So we can know this. And so we can also find that, so here, so because we have this result, so we can say that the inverse transformation of y1 should be equal to x1. Inverse transformation of y2 should be equal to x2 because they are 1 to 1 and on 2. Okay? So right now what we are going to prove is that because we want to prove it's linear, so we need to prove inverse transformation of Cyy1 plus y2 will be equal to C inverse T inverse y1 plus T inverse y2. If this is true, then the inverse transformation is linear. So here we can just apply. We can just replace y1 by t sub x1. Replace y2 by t sub x2. So we have inverse transformation t sub x1 plus t sub x2. Okay, and because we have already know that t is a linear transformation, so ct x1 plus ct plus tx2 will be equal to t on the transformation on cs1 plus x2. So we have this one. Okay, and also we know that because t inverse is the inverse transformation of t, so the composition of these two transformations should be identity transformation, so which will be equal to cs1 plus x2. But x1 we know x1 equals inverse transformation of y1, x2 equals inverse transformation of y2. So then we have we replace x1 by t inverse y1, x2 by t inverse y2. Then we have c times inverse transformation of y1 plus inverse transformation of y2. So then we finish this proof. Okay, so theorem 2.17 is simple. So then the next statement is that if T is a linear transformation between vector spaces of equal dimension, then the conditions of being invertible 1 to 1 and on 2 are all equivalent. Actually, it follows the theorem 2.5. It follows theorem 2.5. So we can say that if it's we can also say that if the transformation is invertible, then it implies that the transformation is 1 to 1 and on 2, and also the two vector space are with the same dimension. Okay, so all these statements are equivalent. Okay, but the most important thing is that this transformation should be invertible. If it's invertible, then it implies 1 to 1 and on 2 and also equal dimension. And then we define the matrix. Because from this course, how we follow that we have the transformation first. Then because of transformation, we have matrix representation. Okay, so here, so right now it's very straightforward that if I have this transformation, then I can have a corresponding matrix. So I have invertible transformation, then I have invertible matrix. And in addition to that, this matrix should be a square matrix because from V to W, both vector space are with the same dimension. So here I have a matrix A. It's a n by n matrix, and the A is invertible if there is another n by n matrix B such that A times B equals B times A equals the identity transformation. Identity matrix. Okay, so if A is invertible, we can find an inverse matrix of A. Okay, so if A is invertible, then the matrix B such that AB equals BA equals IN is unique. This one is unique. Okay, and so the matrix B is called as the inverse of A, and we denote it as A inverse. So now we have the inverse matrix definition here. Okay. So so right now it's very easy to verify that. Okay, we have a 2 by 2 matrix, and if I have a matrix 5, 2, 7, 3, then the inverse matrix we can find the inverse matrix 3 minus 2 minus 7, 5, and we get the identity matrix here. So the inverse matrix of this matrix is this matrix. And how can we find the inverse matrix? They will be left for chapter 3. Okay. So in chapter 3, we will have a theoretical study on the inverse of a matrix. So the next one, the lemma states that okay, V and W be vector spaces, and the T is from V to W, and it's a linear and invertible. Then V is finite dimensional if and only if W is finite dimensional. In this case, dimension V equals dimension W. So we have already proved it. So we have already proved it in the in what we discuss here. So the two vector space should be with the same dimension. So I'm not going to prove it again here. So I think it's about time to take a break. So let's take a break for 10 minutes. Okay, so now we're going to discuss the theorem 2.18. 2.18. So in theorem 2.18, we said that let V and W be finite dimensional vector spaces with ordered basis beta and gamma. Okay, and T is linear from V to W. And we want to prove that T is invertible if and only if the matrix representation is invertible. And then we want to show that the inverse transformation from gamma to beta, the matrix representation of this inverse transformation will be equal to the matrix representation of T's invertible matrix. Okay, we want to prove it. So here we can still plot it, V and W. So here we have beta. Maybe beta is from V1 to Vn. And the gamma is from W1 to Wn. So because this transformation is invertible, so both vector space are with the same dimensions. So I have W1 to Wn. Then I have a linear transformation of T, which is invertible, so T inverse also exists. T inverse also exists. Okay, so right now what we're going to prove, because from the statement of this theorem, it said that T is invertible if and only if its matrix representation is invertible. So we need to prove that from left to right and then from right to left. So right now what we are going to do first is from left to right. We have already known T is invertible. We have already known it. Okay, so because T is invertible, we know that dimension V equals dimension W. Okay, and so we let the dimension V equals N, and so then beta contains N linearly independent vectors, and also gamma in W also contains N linearly independent vectors. So right now T is from V to W, and we can represent its matrix representation as this one. Okay, the inverse transformation is from W to V, so we can represent its inverse transformation matrix representation as gamma to beta. Okay, so we have this. So because we have already known that, I don't need to write it again. So we have already known that T inverse equals IW. T inverse T equals IV. So because IV and IW, if we use a matrix to represent them, then both of them are N by N identity matrix. So we can know that IN will be equal to IV from beta to beta. And the IV can be decomposed as T inverse and the T from beta to beta. And then we have to apply theorem 2.11. What does theorem 2.11 say? Sorry, the previous one. Okay, what does theorem 2.11 say? 2.11 says that if I have a composition of linear transformation and we use a matrix to represent this composition of linear transformation, then this matrix can be equal to the matrix representation of U times matrix representation of T. So in theorem 2.11, we have already proved this. So then we have here. So T inverse is from gamma to beta. Sorry. T inverse is from gamma to beta. And the T is from beta to gamma. We can have this equation followed by theorem 2.11. So then we know that T inverse from gamma to beta will be equal to T from beta to gamma's inverse matrix. Okay, so because you can consider it as A and the B, and the A will be equal to inverse matrix of B. So we get this result. So here the matrix representation of the linear transformation is invertible. So we can get this result. And the same way we can get T from beta to gamma, T inverse from gamma to beta equals IW. Okay, so we can get this result very straightforward. And right now, what we are going to prove is that okay, right now we know that T from beta to gamma is invertible. So what we have is T from beta to gamma times inverse matrix from gamma to beta equals IN, and also T inverse from gamma to beta, T from beta to gamma equals IN. So we have already known this. Right now we want to prove T is invertible. So we want to prove it in the reverse way. Okay, so I don't quite like the proof available in the textbook, so I will use my own way to prove it. Pretty similar, but I think it will be more clear. So here, we want to prove that T is invertible. If we want to prove T is invertible, then what do we need? We need to prove that inverse transformation of T sub Vj equals Vj, because T inverse T, the composition of these two transformations should be equal to identity transformation. So for any vectors in vector space V, after this composition of linear transformation, we get it back to Vj. So if this is true, then we call that this transformation is invertible. So first thing is that because we know we have already had this transformation, so no matter whether this transformation is linear or not, we can always find a matrix representation of T, and we denote it as A. We haven't known the inverse transformation exists yet. Right now, this is what we are going to prove. So the first thing is that we have already known this one exists, and we can always take its matrix representation, and we define this matrix is A. So here, we define the matrix representation of T should be A, and right now, because from the statement here, this matrix representation is invertible, so A is invertible. So because A is invertible, so we can know that if A matrix is invertible, then there exists an n by n matrix B such that AB equals BA equals IN. Because we know this matrix is invertible. So the matrix representation, the matrix is, we can find the B matrix, but right now we haven't known what B is. So we may need to know that, we may need to find what B is. Okay, so right now we know AB equals BA equals IN. So we have BA, and BA we operate the product of two matrices, two n by n matrices. So we can write B as B11, B12 to B1n, B21 to Bn1, and to Bnn. And also A, we can write all of them. And then we take one of the elements, kth row, and the intersection of kth row and the jth column. So the kth row and the jth column's element can be expressed as summation I equals 1 to n bkj, bki times aij. So we can have this result by the definition of matrix multiplication. Okay, so now what we are going to do is that, okay, we have already known that we assume beta consists of V1 to Vn, which is the basis of vector space V, and the gamma consists of vectors from W1 to Wn, which is the basis of W. So we can let beta and the gamma, we can find the beta and the gamma. So what we are going to do is that, okay, right now we will define a transformation U from W to V. We will define a transformation U from W to V. So right now, because we know we have a transformation from W to V, so we can find a corresponding corresponding matrix representation of U from gamma to beta. But this one is unknown yet. We have to find what U will be. Okay, so by definition, right now by definition, we know T is from V to W. So we can always express T, so Vj equals summation I equals 1 to N Aij times Wi. We can always express it in this way. Okay, because we have already defined the matrix representation beta to gamma equals A. We have already defined it. So we can always write it this way. And right now we have another transformation U from W to V. We have no idea what U will be, but right now from this definition we have U, so Wi will be equals to summation K equals to 1, K equals 1 to N, and then it will be written as the matrix representation of U from gamma to beta. We take Ki times Vk. We take Ki times Vk. Okay, so we can write it in this way. We can define it. And then this matrix is what we are looking for. So right now, if we combine these two transformation together, if we have the composition of linear transformation of UT, if we have the composition of linear transformation of UT, and then we operate it on Vj. So by definition, we have U have T operate on Vj. But from here, this one is known already. So I can have U, so TVj can be replaced by summation I equals 1 to N Aij times Wi. Okay, we can replace it, but we also know that U from W to V is linear. So because this transformation is linear, so I can write it as summation I equals 1 to N Aij and operate U on W. So we have this one. And then by this definition, this is what we are looking for. By this definition, we can write it as summation I equals 1 to N Aij times summation K equals 1 to N, and the matrix representation of gamma Ki times Vk. Okay, so right now what we are going to do is we change the order, the do loop order of this summation. So we can take K to the outer loop, K equals 1 to N. And then in the inner loop, I have summation I equals 1 to n aij times u gamma to beta ki. Then we have this summation as a coefficient of vk. Okay, we can have it as of vk. And right now, then what we are going to do is we just change the order again. So we have summation k equals n, or 1 to n, and the summation I equals 1 to n u gamma to beta ki times aij. And then this is the coefficient of vk. Okay, so right now, what we are going to do is that, so we convert any vectors in basis back to this vector space V. So we transform it, first we transform it to W, and then transform it back to U. And because we know T is invertible, so there exists some transformation such that this one will be equal to Vj. This one will be equal to Vj. That is to say, ut Vj equals I Vj equals Vj. So we exist this transformation. So right now, what we need is that, so we need to have, because if the T is invertible and the U is inverse transformation, then we should have summation I equals 1 to n u gamma beta ki times aij. It should be equal to delta ij. It should be equal to delta ij. Okay, so let's look at here. Let's look at here. So ut of vj equals ut of vj, and then we replace tvj by this equation, this linear combination. And then because of linear transformation, I can have this one, and then this one, and then this one. We have this one. So because A is, right now, the important thing is that A is invertible, because the matrix A is invertible. So then right now, what we are going to do is that we will assign B, which is the inverse matrix of A, because A is invertible. So there exists an invertible matrix B such that BA equals AB equals I equals the identity matrix of identity matrix. Okay, so we assign this one. We assign this one. And then we assign this one and denote it as this one. Okay, so from theorem 2.6, what does theorem 2.6 means? Okay, we just has a classmate asked what does theorem 2.6 means. 2.6 means that in theorem 2.6 it states that, okay, whatever vector space V and W, I have V1 to W1, V2 to W2, to Vn to Wn. Whether W1 to Wn are identical or not is not important. If I have one vector in V and one vector in W, and we have the correlation, this correlation is T. So there always exists only one transformation such that TVJ equals WJ. No matter W1 to Wn are linearly independent or not. Once I have this one-to-one response, then we can always find this linear transformation, and is it only one transformation? Okay, so for example, if I have a transmitter and if I have a receiver, So if I send to V1, if I send X1, I receive Y1. If I send X2, I receive Y2, and etc. If I test it for n times, and I receive Yn, then I can always find a relationship between Yi and Xi by using a transformation. And this transformation can be represented as a matrix. This transformation can be represented by a matrix. Okay, so if I have an input and an output, I can always find the transformation between these two sets of data. Okay, one is known data, the other one is measured data. And I can always find only one transformation between these two sets of data. Okay, so that is what theorem 2.6 means. Then, so here, from theorem 2.6, we know that I can always find the matrix representation of U, and we define this U, the matrix representation of U equals B, and B is the inverse matrix of A. B is the inverse matrix of A. And because B is the inverse matrix of A, so if I take summation I equals 1 to n bki times aij, if we do this do loop, then we can find the coefficient of Vk here. And because this matrix is the inverse matrix of A, so the coefficient here should be delta kj. And the delta kj equals 0 if k is not equal to j. Delta kj equals 1 if k is equal to j. So then we have summation k equals 1 to n delta kj times vk, then we can have only one vector left, which is vj. So when a matrix representation of U from gamma to beta equals B, then UPVJ equals VJ, and which will be equal to identity transformation of VJ. Then UP is IV, UP equals IV, and then U is the inverse of T. And the same approach, we can prove that TU equals IW. So then, if T is if T is invertible, this matrix representation is invertible, then T is invertible. Okay, so right now what we are doing is that, so from the theorem, what does it say? What does it tell us? It tells us that from it tells us that, I have a vector space V and the W. Okay, and I have already known T. So right now, we don't know what is T inverse. What can we do? How can we find the T inverse? So the first thing is that, the first step is that, T, we can represent it. T is converted to the matrix representation, which will be A. And because A is invertible, so in chapter 3, we will learn how to find BA equals IN. From this one, we can find B. We can find the B. Okay, we can find the B. And when we find the B, then we can know B, we can let B equals to T inverse gamma to beta. And from this matrix, we can find T inverse back. So the ultimate goal is to find what will the inverse transformation look like. What will the inverse transformation look like? So why do we need to do this? Why do we need to do this? Because because in many transmission system, many communication transmission system, because I'm with Communication Institute, so I will give an example in communication systems. Okay, so I have transmitter and I have receiver. So at the very beginning, we don't know what where this transmission system is. We don't know what is it. We don't know what is it. So if I transmit a signal A, what will I receive? I don't know at all. I don't know anything at all. So the first thing is that we transmit known data K1, X1, X2 to Xn. We transmit the known data. These data are already known by the receiver. The receiver had already known this. So then, when I transmit X1, then I will receive T sub X1. Because we assume this transformation as T, and then we receive T sub X2, and then we receive T sub Xn. So here, this is what we measured. This is what we measured. And by theorem 2.6, it says that whatever X1 corresponds to TX1, whatever receive TX2 corresponding to this X2, I can always find this transformation. Is it only one? So we have already known X1, X2, Xn, and then what we receive is this. So right now, what we are going to do is we are going to find T representation from beta to gamma. We can always find it. Because from this transformation, we can always find it. Okay, we can always find this kind of relationship. Then, if I have this relationship, next one, if I have A1 X1 plus A2 X2 plus AN Xn, if I have any X transmitted, then receive will be T sub X. Because through this data, we know this already, and we obtain these values, then we can find this matrix. By using the matrix representation, we can find this matrix. And then later, any arbitrary signal comes in, we receive this arbitrary signal out. Then we can write it as, if we respect to gamma, I can write as T beta to gamma times y with respect to gamma. If y is the receive matrix here, and then we can find here because we can find this one. So whenever I receive this y, if I apply, sorry, here x, sorry, as respect to beta. Okay, so this is what we received with respect to y. So when I receive this one, I know that T beta gamma x with respect to beta. This one it has been calculated from this information, from this linear transformation. Then we have already known it. This one is unknown because in the transmission system, in the communication system, we don't know what we receive yet. And this is what we measured, what we received. So we know this, we receive this, and we have already calculated this, and which is matrix A, but we don't know this one. So how can we know this one? We can always use the inverse matrix B such that B times the Y with respect to gamma, which will be equal to B times A times X matrix, X vector here. Because B is the inverse matrix of A, so I have identity matrix here, so I get XB as the inverse matrix times the received signal. Then I get the original data. So that's the way we recover the received signal. Even though we don't know what we're going to receive in advance, even though we don't know what will the original data be in advance. But because we have already known this matrix, then from this matrix we can find inverse matrix here. Or we can find inverse matrix here, which equals A inverse. We can find inverse matrix. And then we know this inverse matrix, we apply it on the received data, we can get the original data. So that's why we are going to use this approach. OK, 好，那这个地方跟各位讲的一个就是说，当我今天在这个定理里面我用中文再讲一次，就当我在这个定理里面，我们今天在一个通讯系统里面，传输端，假设我先传一个已知的讯号过去，接收端也知道的东西。所以我传 S1， 接收端收到是这个 1 这个东西，但是他知道你传什么东西。那传 S2， 我接收到 T 扫 S2， 传 SN 我接收到 T 扫 XN。那传的东西我已经知道，那接收到的我现在当场量到的我也知道，所以我可以从这些资料，从定理 2.6 里面找到这个 T 是什么东西，而且只存在一个，好，就是定理 2.6 所讲到的。好，定理 2.6 所讲到的这个东西，好，所以我们在 W1 到 WN 我接收到的有 W1 到 WN， 但是 V1 到 VN 是我用已知的讯号去传，所以我要接收到这个讯号，然后呢，我现在接收到的我已知我要接收到的原始讯号是这个，但是我现在接收到是这个，所以我可以从这2组讯号里面去找到这个矩阵。好，可以去找到这个矩阵。那这组讯号我们把它叫做，在通讯系统里面我们把它叫 training symbol。好，叫做测试的讯号。好，那这是已知的，接收端跟传输端都已知。那已知的在接收端这一段呢，我就可以知道从这个地方呢，我去估测到说我这通道响应的矩阵长什么样子。那知道这个矩阵长什么样子呢？我们从矩阵的运算，我们可以找到在第3章的时候，我们可以找到它的反矩阵是什么样子。我们可以知道它的反矩阵是什么样子。所以当今天我任何一个信号，一个任意的讯号 x 过来的时候，那 x 呢可以表示成为这些基底向量已知讯号的线性组合。那所以我就可以找到这个 x 它的基本向量，它的坐标向量。那这坐标向量我们这个时候其实是我不知道的，因为我接收到是这些所有向量这些所有讯号的 linear combination。所以我不知道，其实我不知道 x 这是什么东西，但是那是我要去求的。所以这时候我接收到的时候是 y， 这时候 y 呢已经被所有的讯号这边 A1、A2 这些东西给搞得很混乱了。那我怎么样知道说这 A1 跟到 AN 是怎么组合的呢？我可以知道说，因为从我原始的训练资料知道，我送第一个基底向量，我得到这个；第二个基底向量得到这个；第3个基底向量，第2个基底向量得到这个。所以经过这个矩阵运算，说我接收到的，我可以去求到这个 A 是什么的时候，那这个时候变成我们已经去计算出来，我已经知道了。所以这时候我接收到的讯号等于是这个 A 矩阵乘上这个我未知的 X 矩阵 X 向量，这个是 what we are looking for。我不知道的东西，但是 A 我已经知道了，而且 Y 是我收到的，我接收到我已经量测到了，所以呢我就乘上一个，因为我已经知道 A， 所以我可以去找到 A inverse。所以我乘上它的 A inverse 上去，直接乘 A inverse 上去 ，A inverse 上去 ，A inverse 跟它 A 就直接消掉，剩下来就是我们所要找的这个讯号 information。好，所以我们现在的通讯系统都做这个事情，我要去做。那这个过程，这个去找 A 的过程，我们把它叫做 channel estimation。我们把它叫做通道估测。我要去做通道估测。好，我去做通道估测。那通道估测做好之后，去找到这个 B， 这个 B 我们叫做 equalization。好，那这个 equalization 就是我去把这通道响应给去掉。好，通道响应给去掉，所以这个过程叫做 channel estimation and equalization。 经过 channel estimation 的 equalization， 我可以找到一个适当的 inverse matrix B， 然后我就把我进来的讯号的各个权重把它给去掉，得到因为通讯系统所得到这个权重把它给去掉，得到我原始的讯号是什么。好，所以我们在这一章里面，在这一个地方讲的这件事情，其实在通讯系统里面是非常重要的一个概念。好，通讯系统里面非常重要的一个概念。好，所以这边再跟各位解答定理 2.6 在讲什么。定理 2.6 就是讲说，我今天接收到这个讯号，但是我传的讯号我已经知道，所以我永远可以从这个已知的讯号，从已知要传什么东西，我接收到讯号这之间的关联性，我找到这一个转换当中它这里面发生什么事情，用矩阵的方式表示出来。好，用矩阵的方式表示出来。好，那这是这个定理非常非常重要的一个部分。OK。那当然，我们在这边讲的是 n 乘 n 的矩阵。那实际上，在通讯系统，大部分很多不是 n 乘 n 的矩阵，所以我们 n 乘 n 有反矩阵 ，m 乘 n 就没有反矩阵。这时候以后我们就要学到一种东西，叫做 pseudo inverse matrix。好，虚假的这个反矩阵。好，那这个是在第6章的部分会讲到 pseudo inverse。好 ，OK。So we finished theorem 2.18, and now from the corollary。Corollary 1 and corollary 2, which are similar to theorem 2.18, so we are not going to prove it. So here we just change we just narrow down its application. So in theorem 2.18, it's a general case. So we have two distinct vector space, but in corollary 1, we have only one vector space. So V be a finite dimensional vector space with ordered basis beta, and the T is the transformation from V to V. So we transform the vectors within the same vector space, and then T is invertible if and only if the matrix representation of T is invertible. And so then furthermore, the inverse T's matrix representation will be equal to the matrix representation of T's inverse. Okay, so this one we just narrow down the application. So from here, we don't need to demonstrate that the dimension V equals dimension V because it's true. So we don't need to say that okay, V has the same dimension as W because we have the domain and codomain identical. Okay, and then the next one, okay, we have learned what is left multiplication transformation. So LA, which LS of X equals AX. A is the n by n matrix. So A is invertible if and only if the left multiplication transformation is invertible. Okay, so this one is also easy, and we're not going to prove it. But but here what we are going to discuss is that so what does LA means the left multiplication transformation? What does the left multiplication transformation means? Okay, so the left multiplication transformation is the way we apply this linear transformation theorem. So here we have original vector space V, and we have another vector space W. Okay, so right now I have a set of vectors beta and a set of bases, and the gamma is the basis. So we have linear transformation here, T. So typically we have to write Tx1, Tx, which will be in W. And then we have V1 to Vn. So we have to write TV1 equals summation I, TV1 equals, maybe TVJ equals summation I equals 1 to N Aij times Wi. Okay, so what we are doing here is that actually we first, for the left multiplication transformation, we first take any vector here. We take any vectors with respect to the basis order. Then what we get is a coordinate vector. So I can have A1, A2 to AN. So we can, because x can be expressed as a summation I equals 1 to n ai vi. So when we take its coordinate, what we get is the coefficient on each individual basis vectors. So I have a2 to an. So right now we transform a vector, a general vector into a coordinate vector. So this is what we are familiar with. So then we transform it. By using this approach, we transform it to the n-tuple column vector. The n-tuple column vector. Then we transform it by using a left multiplication transformation LA, and then because right now x is in a vector here, then we have LAX. X is in the coordinate vector. Then we will receive y with respect to gamma. So then we have Fm here. We have Fm here. Then here I can get the coordinate of the coordinate vector after the transformation. So right now, because it's with respect to gamma basis, so if y I have b1, b2 to bm, then what do I have in the vector here, y? We just write y as a linear combination b1, w1 plus b2, w2 plus etc. plus bm, wm. So the left multiplication transformation is that we try to transform the linear transformation into a matrix approach. So in addition to directly apply this transformation, we can go this direction, because this direction can be done by computer. Because computer is good at do loop calculation, this kind of routine calculation. So the matrix calculation is best done in computer, not by yourself. Okay, so especially if you have more than 2, 3, 4, 5 loops, then you let computer to do it. It will calculate. It will give you a very accurate result. So we just transform the transformation system by using the matrix operation, by using this approach. Okay, so that's what the left multiplication transformation doing. Okay, now, so we define another one. So right now here we want to define that, okay, V and W be vector spaces, and we say V is isomorphic to W if there exists a linear transformation T is from V to W that is invertible. And in such a linear transformation, we call them as an isomorphism from V to W, V onto W. So this means that, okay, if I say the two vector spaces are isomorphic to each other, they are isomorphic to each other. So here, V and W. So we have a vector space V and W. Okay, if we solve this, if we say V and W are isomorphic, which means that there exists some linear transformation. This transformation is linear and invertible. So T inverse exists. If this condition is true, then V and W is to be isomorphic. T and W is to be isomorphic. So what does that mean? Because we have the transformation, which is invertible. So then isomorphic means that dimension V equals dimension W. Okay, because it exists an invertible linear transformation here. So whenever we have an invertible transformation, the two vector spaces should have the same dimension. Should have the same dimension. So if V and W are isomorphic, then their dimensions are the same. And so here, then we call this transformation as isomorphism. As isomorphism. 好，那 isomorphism 在中文上面叫同构，同样构造。那这两个向量空间是同构的，好，同构的，因为它的维度是一样的，因为它存在着一个逆转换 invertible 的 transformation。好，所以如果说，所以这是一个 definition。好，所以 V and W be vector space。And we say that V is isomorphic to W if there exists a linear transformation T which is invertible. So we have an invertible transformation. And so because we have an invertible transformation, so dimension V equals dimension W. We have already proved it. So such a linear transformation is called isomorphism from V onto W. Okay, so we define this isomorphic and isomorphism. All right, and then the example is that, okay, if we just take what we have done here, if we just take the coefficient from a degree 2 polynomial into a coordinate vector, then, we transform the coordinate vector into a degree 1 polynomial. So if I have a set of coordinate a1, a2, then we transform into a1 plus a2x, just like what we have done here. We have the coordinate vector here, and then we transform it back to the vector space W by using some kind of transformation. And this kind of transformation is isomorphism because they are with the same dimension. Okay, so it's easy to see that the T is linear and invertible. Okay, and then T is isomorphism, and the F2 is isomorphic to P1F, to the degree 1 polynomial. So we can learn it very easily. So now we have theorem 2.19. Let me see. Okay, 2.19 says let V and the W be finite dimensional vector spaces, and the V is isomorphic to W if and only if dimension V equals dimension W. So from left to right is very straightforward because V is isomorphic to W, which means that there exists invertible transformation. And if any invertible transformation exists, then dimension V should be equal to dimension W, which is very easy to be proved. And now we have to go back from, if we know dimension V equals dimension W, then V is isomorphic to W, which means that I have to prove that there exists a linear, an invertible transformation. Because if we want to prove V is isomorphic to W, we have to prove that between these two vector spaces, there exists an invertible transformation. Okay, so we have to prove, first of all, we have to prove is this a linear transformation that is invertible. Second, first of all, we need to prove that there is a transformation. Second, we need to prove it invertible. Okay, but it will take much longer time, so we will just stop here, and we will leave the rest of them on Friday. So right now I want to discuss with you about the midterm time, because according to the syllabus, the midterm will be scheduled on next Friday. But I expected that following the course progress, actually, in my syllabus, I will finish chapter 2 on next Wednesday. So right now we are on the steps, but we are on the path. But right now I'm afraid that if I finish the course, the chapter 2 on Wednesday, you have only 2 days to prepare for the midterm. So I will postpone the midterm by 1 week. Postpone the midterm by 1 week. So right now the midterm day will be changed from, let me see. So we will postpone it to November 4th. 好，因为我们上课的时间，因为如果我们按照表定28号考试的话，因为我们现在剩下的讲义大概是，我们现在讲义大概还需要上2次左右，才能够完整的讲完。好，我们现在剩下大概10页左右，大概会2次。到下礼拜三的时候，我会进到第3章。好，那可是这样子的话呢，各位准备考试的时间只有2天，最后面这边的话，你可能只有2天的时间准备。好，所以我们把时间可能延到11月4号，怎么样？有什么问题吗？还是你们只能够11月4号或者是10月28号？啊？第2次段考是不是11月23号？因为第3章、第4章非常简单，你们都学过。第3章、第4章，你如果去看讲义的话，第3章、第4章都是你们学过的东西哦。第3章，因为以前我们的经验的话，第3章、第4章可能1个礼拜，这大概差不多1-2个，大概这个基本的这个矩阵的操作、线性系统这个东西你们都知道。好，这些东西矩阵的操作你们都知道。好，线性转换这些东西你们都知道，而且页数不多啦，大概这边只有虽然说38页，但是很多东西你们都知道。好，那第四章的东西是我看一下第4章。好，3、4章的话都是你们以前学过的行列式值，这个是你们学过的行列式值。好，行列式值大概我们只教1个礼拜就可以结束了。好，行列式值，所以这个部分虽然有26页，其实说有很多东西可以不用教，你们都学过，所以第3章、第4章实际上是你们很熟悉的东西，所以不太需要花很多时间。好，所以我预计就是11月4号考这个第1章、第2章。好 ，OK， 好，那大概今天就到这个地方。会比期末考还爽一点啊！期末考更惨啊！